At the end of his famous dialogue, Galileo lists what he considers to be his 3 best arguments for proving that the Earth moves around the Sun. One of these is his argument from the ebbing and flowing of the ocean tides, high and low tidal water. Galileo believed the tides were caused by the motion of the Earth. This is truly one of his worst theories. He was so proud of it, but it stinks, and I will tell you why. But first things first, how do the tides work actually? As we know today, the ebb and flow of the sea arise from the action of the sun and the moon. That's Newton's accurate statement of this correct explanation for the tides. They are a consequence of gravitational forces, as Newton proved. The moon, and to a lesser extent the sun, they pull the water toward them, causing our oceans to bulge now in one direction then the other. This was clearly understood already in Galileo's time, long before Newton. Kepler explained it perfectly, as did many others. Proposed the lunar attraction theories of the tides that were commonplace at the time. In fact, the lunisolar theory of the tides is found already in ancient sources in Greek times, including these sources even specify the causal role of the sun and the moon. They describe the effect in extensive and accurate detail. There's just no two ways about it. Galileo, however, got all this completely wrong. Why should the tides of the seas follow the movements of the fireballs in the skies, as Kepler had put it? Galileo considered the very notion childish and occult, and declared himself astonished that Kepler, enlightened and acute thinker as he was, listened and assented to the notion of the moon's influence on the water. Those are Galileo's own words. Continuing in his treatise, Galileo writes, "There are many who refer the tides to the moon, saying that this has a particular dominion over the waters, and that the moon, wandering through the sky, attracts and draws up toward itself a heap of water which goes along following it." Yes, indeed, many people believed such things, and they were right. Galileo would have none of it. This theory is not one which we can duplicate for ourselves by means of appropriate devices, he objects. And how indeed could we ever make the water contained in a motionless vessel run to and fro or rise and fall? Well, certainly not by moving about some heavy rock located many miles away. But if, says Galileo, by simply setting the vessel in motion, I can represent for you, without any artifice at all, precisely those changes which are perceived in the waters of the sea, why should you reject this cause and take refuge in miracles? That's Galileo's objection to the lunar theory of tides. It's hocus pocus. It assumes the existence of mysterious forces that we cannot otherwise observe or test. Proper science should be based on stuff we can do in a laboratory, like shaking a bowl of water. Actually, I think this argument is really not half bad as far as it goes. How is the moon supposed to influence the oceans across thousands of miles of empty space? What reason do we have to believe that such a force exists? It doesn't fit any common sense knowledge that we have. It doesn't fit with any empirical experience. It's a wild idea. It's a kind of mysticism. But maybe that's the lesson of the story. Sometimes wild ideas are right. Rational scientific prudence is not all it's cracked up to be in every situation. It's a good thing that we had some Keplers who said, why not, instead of only Galileos who said, don't be silly. A childish and occult theory based on miracles, yeah, so that's what Galileo thought of the lunar theory of tides. He put it in so many words literally, those are direct quotations, and with good reason. But he was wrong. The world really is occult, it turns out. Maybe nowadays we've been brainwashed into thinking that the moon's pull on the oceans is just science, you see. There's nothing weird about it, But isn't it just as occult as it ever was? Isn't that what science is actually? A bunch of occult stuff that we have gotten so used to that we've given it another name. By the way, if I may territorialize a little bit further here, don't we have a lot of mini Galileos running around today? All these self-proclaimed rational disciples of science are out to tell you about all your dumb beliefs being nothing but childish faith in occult miracles, just as Galileo would have it. Think of stuff like vaccines causing autism, homeopathy, creationism. There's an army of little Galileo clones waging war on those occult things, isn't there? And perhaps it's worthwhile to remember on such occasions that Galileo was just as sure with his argument about the tides in the bucket. But, well, enough about that. Now, if Galileo didn't believe any of that stuff about the correct theory of the tides, what did he believe then? So let's turn to his own theory of the tides. I like to think of it in terms of a torus, as we say in mathematics. So it's a ring, like a hollow donut, or one of those inflatable rings that children put around their waist when they go playing in a pool. So to understand Galileo's theory, you should picture one of those rings, a torus, filled halfway with water. So it's laying flat on the ground. The bottom half of it is filled with water, and this represents the water encircling the globe of the Earth. And now you take this torus and you spin it. You spin it in its place around its midpoint like a steering wheel. This represents the rotation of the Earth. So what's going to happen when you spin it like that? For symmetry reasons, it is clear that the water will not move, because there's no reason why the surface of the water should become higher or lower in one place of the tube rather than another. And every part is rotating equally. Everything is symmetrical. No asymmetrical distribution of water could arise from such a process, But now here's a further complication. Picture the torus now sitting on a merry-go-round. Well, this represents the Earth orbiting the Sun. Also, at the same time, it's also spinning around its midpoint like before. Now, this produces indeed an asymmetry in the configuration. The torus, it has one part facing inward toward the middle of the merry-go-round and one part facing outward. And as far as the rotation of the torus around its midpoint is concerned, these two parts of the torus are moving in opposite directions. But as far as the rotation of the merry-go-round is concerned, they are both going the same way, of course. So one part of the torus spins along with the orbital motion, and one part goes against the orbital motion, and therefore one part of the water moves faster than the other. It is boosted by the merry-go-round rotation, helping it along in the direction that it was already going, while the other part of the torus is slowed down because the merry-go-round is cancelling its effort by going the opposite direction. So you have then fast-moving water and slow-moving water, and the faster-moving water is going to catch up with the slower water and pile up on top of it, creating a high tide. And the space it vacated will not be replenished because the slow water behind it isn't keeping up. So you have the low tide. And here's how Galileo puts it. Mixture of the annual and diurnal motions causes the unevenness of motion in the parts of the terrestrial globe. Upon these two motions being mixed together, there results in the parts of the globe this uneven motion, now accelerated and now retarded by the additions and subtraction of the diurnal rotation upon the annual revolution. And therefore, in fact, the flow and ebb of the seas endorse the mobility of the Earth. That's Galileo's conclusion. This was one of his favorite arguments. Unfortunately, Galileo's theory is completely out of touch with even the most rudimentary observational facts about tidal waters. High and low water occur 6 hours apart. In the lunisolar theory, this is explained very naturally as an immediate consequence of the basic principles of the theory, namely as follows. The rotation of the Earth takes, of course, 24 hours. There's a wave of high water pointing toward the moon, basically, give or take a bit of lag in the system. And then there's another high water mark diametrically opposite to that on the other side of the Earth. So that's two high and two lows in a 24-hour period, making 6 hours apiece. Galileo's theory, on the other hand, implies that high and low water should be 12 hours apart rather than 6. These are his own words here. There resides in the primary principle no cause of moving the waters except from one 12-hour period to another. So Galileo himself immediately he finds himself on the back foot. He has to somehow talk himself out of this obvious flaw of his theory. And to this end, he alleges that the particular events observed regarding the tides at different times and places are many and varied. These must depend upon diverse concomitant causes, such as the size, depth, and shape of the sea basin, and the internal forces of the water trying to level itself out, things like that. So the fact that everyone could observe 2 high and 2 low tides per day, Galileo just wrote off as purely coincidental. He explicitly says exactly this. Here is his quote. 6 hours is not a more proper or natural period for these reciprocations than any other interval of time, though perhaps it has been the one most generally observed because it's instead of our Mediterranean. And Galileo, in fact, even has some fake data to prove this erroneous point, namely that tides 12 hours apart are daily observed in Lisbon, he believes, even though it's completely false. And there's also a further complication involving Galileo's theory, which caused the embarrassment of his more competent readers, as one historian puts it. The inclination of the Earth's axis implies that the effects that Galileo describes should be strongest in summer and winter. And unfortunately for Galileo's theory, the reverse is the case. Actually, the tides are most extreme in spring and fall, because of that's the moment when they receive the maximum effects of the sun's gravitational pull, conspiring with the moon at those times. Now, Galileo, he got himself confused on this point, because he was relying on false data. Galileo, of course, the self-declared enemy of relying on textual authority, who often mocked his opponents for believing things simply because he said so in some book. He was in fact the one, in this case, who found in some old book the claim that the tides are greatest in summer and winter, and he took this for a fact and derived this supposed effect from his theory. The mismatch between Galileo's theory and basic facts is on display in another episode as well. Galileo attacked those who postulated that an attractive force acted from the moon on the ocean for failing to realize that water rises and falls only at the extremities and not at the center of the Mediterranean. Well, actually, his opponents can hardly be blamed for failing to detect this so-called phenomena. Actually, it only exists as a consequence of Galileo's own theory. Galileo, he was so biased by his wrong-headed theory that he used his erroneous predictions as so-called facts with which to attack his opponents who were actually right. Actually, all of the above is still not yet the worst of it, believe it or not. There's an even more fundamental flaw in Galileo's theory, namely, it is inconsistent with the principle of relativity that he himself espoused, that he's famous for, that carries his name. Think back to that famous scenario where he envisioned the scientist locked in a cabin below deck of a ship that may or may not be moving at constant velocity. Galileo's conclusion on that occasion was that there is no physical experiment that can detect whether the ship is moving or not. But with the torus tidal simulation, if it really worked as Galileo claimed, then you certainly could detect such a motion. You put the torus on the floor of the cabin, you spin it. One part is spinning with the direction of motion of the ship, and the other part is spinning against the motion of the ship. So high and low water should arise by the same logic as in Galileo's tidal theory. If the ship stood still, obviously no such effect could be observed. So, well, there you have it. You have a physical experiment for detecting whether the ship is moving or not, which is supposed to be impossible according to the principle of relativity. And indeed it is impossible, but if that's so, then Galileo's theory of the tides cannot possibly work, because it is inconsistent with this principle. This objection against Galileo's theory was in fact raised immediately already by contemporary readers. Here's what one contemporary wrote to Galileo in 1633. He's reporting on the reflections on Galileo's book by a group of scholars who had studied it. Quote, "They draw attention to a difficulty raised by several members above the proposition you make that the tides are caused by the unevenness of the motion of the different parts of the earth. They admit that these parts move with greater speed when they go along with the annual motion than when they move in the opposite direction, but this acceleration is only relative to the annual motion. Relative to the body of the earth, as well as to the water, the parts always move with the same speed. They say, therefore, that it is hard to understand how the parts of the earth, which always move in the same way relative to themselves and to the water, can impress varying motions to the water," end quote. And that is to say, picture the earth moving along its orbit and also rotating around its axis at the same time. So say you hit pause at this animation and you mark two diametrically opposite spots on the equator. Then you hit play again, you let it run for a second or two, and then you pause it again. Now you compare the new positions of the two marked spots with their original position. One will have moved further than the other. But that's in a coordinate system that doesn't move with the Earth. Now that type of inequality of speed is irrelevant. What is needed to create tides is a different kind of inequality of speed of the water, namely a difference in speed relative to the Earth itself and to the other water. Tides arise when the fast-moving part of the water catches up with the slow-moving part of the water. But that is to say, these waters are fast and slow in their speed of rotation about the Earth. inequality of speed in a coordinate system centered in the Earth, that is. No inequality of this type arises from the motion of the Earth about the Sun. Galileo had no solution to this accurate objection. His contemporaries are right and he's just wrong. His theory is dumb. So, to sum up then, Galileo small-mindedly rejected the correct theory of the tides based on the Sun and the Moon, even though this was widely understood by his contemporaries. He then proposed a completely wrong-headed theory of his own, which is based on elementary errors of physical reasoning that are inconsistent with his own principles. These flaws were readily spotted by his contemporaries, and furthermore, his theory is fundamentally at odds with the most basic phenomena, which he tried to explain away by attributing them to untestable, ad hoc secondary effects. He also adduced several false observational so-called facts in support of his theory that are completely wrong. No wonder many have felt that Galileo's ill-fated theory of the tides is a skeleton in the cupboard of the scientific revolution, as one historian has put it. This is a problem really only if one assumes that Galileo was science personified. If we accept instead that Galileo was an exceptionally mediocre scientist who constantly got wrong what mathematically competent people like Kepler got right, then we see that Galileo's skeletons, they belong only to himself and not to the scientific revolution. So once again, we solve a problem of this type by throwing Galileo under the bus. It's not that the scientific revolution was flawed, it's just that Galileo was. If we restrict ourselves to mathematically competent people, we don't have to deal with this kind of nonsense. I'm going to use the tides to make the transition now from Galileo's physics, which we have discussed at length, to his astronomy. Galileo, as we saw, he wanted to use the tides as a proof that the Earth is moving both rotationally and also orbitally around the Sun. Other people, they were not fooled by this poor argument, and yet leading mathematicians did indeed have the sense to accept Copernicus' vision of putting the Sun in the center. Why was that then? Why did these people become Copernicans? Why did Copernicus believe this? Why did Kepler believe it? Well, certainly not because of Galileo, of course. But what then exactly? Well, arguably, the most compelling reason was that the Copernican system explains complex phenomena in a simple, unified way. Here are some basic observational facts. The planets sometimes move forwards and sometimes backwards relative to the stars. Also, Mercury and Venus always remain close to the Sun in the heaven. In a geocentric system with the Earth in the center, there is no inherent reason why those things should be like that. It would make perfect sense for planets to always move only in one direction, or it would make perfect sense for Mercury and Venus to be wherever in relation to the Sun. But nevertheless, those things I mentioned are the most basic and prominent facts of observational astronomy. In the Ptolemaic system, so the geocentric system of antiquity, these facts are accounted for by introducing complicated secondary effects, strange coordinations, parameter values, beyond the elementary model of simple circles. So planetary orbits, they are not just simple circles, but they are combinations of circles in a complicated way that also happens to be coordinated with one another in particular patterns, like the Mercury and Venus and the Sun, they just happen to go along with one another all the time, just by chance. In the Ptolemaic system, there's no particular reason why those complicated constructions should be just that way and not otherwise. We just have to accept that, whoops, it just happened that way. So Ptolemy, he could account for or accommodate the phenomena, but he can hardly be said to have explained them. The basic idea that planets move in circles around the Earth is on the back foot from the outset. It's inconsistent with the most basic data. It's therefore forced to add individual quick fixes for these phenomena. In the end, there are so many layers of patches. It's like you can imagine a house that consists more of like duct tape emergency fixes than the original foundation. In the Copernican system, it's the opposite. The phenomena I mentioned are here instead immediate natural consequences of the motion of the Earth. It becomes obvious and unavoidable that outer planets appear to stop and go backward. This is because the Earth is speeding past them on the inside in its quicker orbit, making that the phenomena of retarded motion is really merely an illusion, so resulting from the Earth's motion. It becomes obvious and unavoidable also that Mercury and Venus are never seen far from the Sun, because like the Sun, they're always on the inside of the Earth's orbit, so you can never see them opposite the Sun, because then that would imply that they would be outside of the Earth's orbit, which is immediately ruled out by the very structure of the solar system in that situation. So there's no need anymore for ad hoc secondary courses or just so numerical coincidences in parameter values and that kind of thing like Ptolemy used. Instead, these phenomena follow immediately from the most basic assumptions of the system. They are built into the very foundation, and rather than being duct taped onto it. Galileo makes precisely this point in his dialogue. You see, gentlemen, with what ease and simplicity the annual motion made by the Earth lends itself to supplying reasons for the apparent anomalies which are observed in the motions of the 5 planets. It removes them all. It was Nicolaus Copernicus who first clarified for us the reason for these marvelous effects. This alone ought to be enough to gain assent for the rest of the Copernican doctrine for anyone who is neither stubborn nor unteachable. End quote. That's all good and well. Galileo is absolutely right. Although, of course, this point was already 100 years old and common knowledge by the time that Galileo repeated it. But, okay, here now is my fun twist on the story. Compare this story about the Copernican versus Ptolemaic system with Galileo's theory of the tides. In fact, the correct lunisolar theory of the tides explains the basic phenomena in a simple and natural way as immediate consequences of the first principles of the theory. That's exactly the same point that we made about the Copernican system. The correct theory of the tides has exactly the same kind of credibility as the Copernican system. So by Galileo's own logic, this ought to be enough to gain assent. But in the case of the tides, Galileo apparently is the one who was stubborn and unteachable, as was his phrase for those who refused to accept Copernicus, because he in fact insisted on a theory which, like that of Ptolemy, could only account for the basic facts by invoking arbitrary and unnatural secondary causes unrelated to the primary principles of a theory. So it's a sign that your theory has poor foundations if the foundations themselves are good for nothing and all the actual explanatory work is being done by emergency extras that are duct taped on later to specifically fix obvious problems with the foundations. Intelligent people realize this, which is why they turn to the sun-centered view of the universe. Galileo, he paid lip service to the same principle when he wanted to ride on the coattails of those insights. But if he had been consistent in his application of this principle, he should have used it to reject his foolish theory of the tides. Okay, that's it for today. Thank you.